So let's go ahead and let's start talking through this. If you're still copying down your theorems and your corollaries, just kind of listen while we talk through these. So what we talk about today, I think the idea is really very simple, but I am going to warn you guys I had a kind of hard time making the notes because the application of these ideas is just so vast, the things that you can do with them. So I will warn you that I always try to make your notes as similar and as relevant to your homework assignment as I can. But that was kind of hard to do with this section, so just letting you know. Okay, so today we're talking about isosceles and equilateral triangles. So to start off, the main focus I think today is isosceles triangles. Equilateral triangles are kind of thrown in there as well. But an isosceles triangle, a word you've probably heard before even if you're not super familiar with it. An isosceles triangle has two congruent sides. Okay? Now the two congruent sides are called the legs. So the legs of the isosceles triangle. The angle that makes up that those two legs create, it's usually if a lot of times they write isosceles triangles so they kind of sit upright, which would be the top angle, they call that the vertex angle. The base, okay, would be the bottom. So not either one of the legs. You have the two legs and then you have the base. Now, the angles that the base and the two legs make up are called the base angles. So a bunch of different fun words there. Now, we have two theorems related to isosceles triangles. That one is the theorem and the other one is the converse. So I think they're very, very simple, but I think the hard part is just keeping them separate, which is the original and which is going to be the converse. So the first theorem, Theorem 4.3 is the isosceles triangle theorem. So just keep in mind that isosceles triangle is a triangle with two congruent sides. So what Theorem 4.3, the isosceles triangle theorem, says, it starts out with an isosceles triangle. So it starts out saying if AC is congruent to BC. So you have a triangle with two congruent sides, okay? The isosceles triangle theorem says that if you have these two congruent sides, the angles that are opposite of those sides are also congruent. So if AC is congruent to BC, then angle A is going to be congruent to angle B. So an isosceles triangle talks about the sides. Okay, you have two congruent sides, but if the sides are congruent, the angles are also congruent. Theorem 4.4 is going to be the converse. So if you remember, I think from chapter 2, we talked about all of those converse, contrapositive, all of those things. It just means you're going to read it kind of from the opposite direction. So it's going to start with the angles, where the isosceles triangle theorem started with the sides. It says if you have two congruent sides, then the angles are congruent. The converse is going to say if the angles are congruent. So if angle A is congruent to angle B, then the sides would also have to be congruent. So AC is going to be congruent to BC. So the isosceles triangle theorem says if you have an isosceles triangle, you have two congruent sides, then the angles are congruent. The converse says if you have a triangle where two angles are congruent, the opposite sides are also congruent. And for our only proof today, waiting for like an aww, only one proof today. Our only proof today is we're going to prove Theorem 4.3. So we're going to prove the isosceles triangle theorem. So let's go ahead, let's set this up here. So our statements, our reasons, and what we're going to prove here, we have our given. So we have that xy is congruent to xz. So that's my isosceles triangle. I have these two congruent sides. But to kind of help us with our proof, what we're going to do here is we're going to draw a line, a segment from the vertex angle down to the base. And we're going to draw it specifically so that it bisects the vertex angle. So we're going to say that XB bisects angle YXZ. That's just going to help us out with our proof here. So I have my isosceles triangle. I know that these two sides are congruent. What I'm trying to prove is that I'm trying to prove that these angles are congruent. So let's come up with the game plan here. When I draw that line from the vertex angle down to the base, what I've done here, I've kind of created two triangles. See the two triangles? So we know from what we did last week, if I could prove that these triangles are congruent, I know that all of their corresponding parts are congruent as well. So that's what we're going to try to do. We're going to try to prove that the left triangle is congruent to the right triangle, because if these are congruent, then those angles would have to be congruent. Well, in the given, I already have that this side is congruent, right? I have one side. But whenever I draw this line, in the way that line XB bisects this, what else do I have? If this line bisects the vertex angle, what does that do? What does it do? If this line bisects the vertex angle, splits it in half. So what do I know about angles 1 and angles 2? They're congruent. So that's going to be my next statement. Angle 1 is congruent to angle 2, because that's just the definition of an angle bisector. So what I have so far, I have a side, I have an angle. Do I have another side? What's my other side? Yeah, XB, right? I know that XB is congruent to XB. How do you know that XB is congruent to XB? Reflexive property of congruence. So guess what? I have a side, I have an angle, and I have a side. So I can say that yes, these triangles are congruent. So I can say that triangle YXZ is congruent to triangle ZXB because of side, angle, side. And guess what? If the triangles are congruent, all of their corresponding parts are congruent, which is what I'm trying to prove. I'm trying to prove that angle Y is congruent to angle Z. And I know they're congruent because CPCT. Okay, now these three down here, the theorem and the two corollaries, which is a new word for us. A corollary, it is a theorem, okay? So that's kind of the big thing that I don't want you guys to miss. That it is a theorem, it can be proved, but how you prove a corollary it's very, very similar to a previous theorem, okay? So, first of all, we have theorem 4-5, which kind of talks about like what we just did. So theorem 4-5 says if you take an equilateral triangle, like we just did, and if you draw a segment from the vertex angle that bisects the vertex angle, like we just did, okay? We know that these two angles are congruent, but what it also does, when you draw this segment that bisects that angle, this segment is a perpendicular bisector. So it does a couple things, right? It creates two right angles right here, and it also bisects or cuts that base side in half. Does two things, okay? It creates a perpendicular bisector, okay? Now the two corollaries are where we start talking about equilateral triangles. So equilateral triangles are triangles that have three congruent sides. So not just two, but all three sides are congruent. So corollary to theorem 4-3, okay, so that's this one. So theorem 4-3, remember, says if you have two sets of congruent sides, the opposite angles are also congruent. The corollary to theorem 4-3 says if you have an equilateral triangle, so if you have three sets of congruent sides, you are also going to have three sets of congruent angles. So it says if you have an equilateral triangle, it's also an equiangular triangle. So lateral refers to the sides, angular refers to the angles. Okay? And then corollary to theorem 4-4, if theorem 4-4 says if you have two congruent angles, the opposite sides are congruent. The corollary to Theorem 4.4 says if you have 3 sets of congruent angles, the opposite sides are also congruent as well. Okay, so we have all of those things to enjoy. Any questions on any of that? All right, let's get this glued into page 57. This is section 4.5, and we are talking about isosceles and equilateral triangles. Okay, so first thing, I'm going to give you a diagram, and then I'm going to give you some statements. We're going to complete the statement, but then we also have to explain why it's true. So, let's draw a big triangle like this. We will call this triangle R, S, T. And then we're going to add a couple other lines here. So, let's draw a line in the middle down to here, and we'll label that U and V. And let's draw one more line right here, and we'll call that W. Okay, then I've got some other markings to add here. Let's say VW and WS are congruent. And then angle R is going to be congruent to angle UVR, which is also congruent to angle WVS. Okay, so here's the statement we're going to complete. And whenever it says explain why it's true, we're kind of looking at those theorems that we were introduced with today. That would be your explanation. Use one of the theorems of the corollary. So number 1, angle WVS is congruent to. Now, angle WVS, okay, it's marked right here. Now, I know it's marked, and I know that there's 2 other angles that were marked. So I know already that it's congruent to angle R, and it's congruent to angle UVR. I want to find an angle that's not marked. And I think in your homework, it does a better job of finding an angle that's not marked. But in this one, I want to see if I can find another angle other than these 2 that are marked that I know is congruent to WVS. Elijah? Angle WSV. I agree with that. Angle WSV. How do you know that angle WSV is congruent to angle WVS? Sorry. WVS is congruent to angle WSV. Oh, this is the part where it gets kind of tricky because you have the isosceles triangle theorem and you have the converse of the isosceles triangle theorem, right? The isosceles triangle theorem says if you have 2 sets of congruent sides, then the angles are congruent. The converse says if you have 2 sets of congruent angles, the sides are congruent. So you don't have to decide what did you start with. Did you start with congruent sides or congruent angles? You started with the sets of congruent sides. You started with an isosceles triangle, which would be the isosceles triangle theorem, not the converse. So we'll say that because the isosceles triangle theorem. Okay, number 2, what if I want UV is congruent to? UV is congruent to. Do I have a side? UR, I agree with that. Yeah, it is congruent to UR. How do I know it's congruent to UR?
Converse of the isosceles triangle.
See, that's the converse because I start with the angles. And if the angles are congruent, so is the sides. The converse of isosceles triangle theorem. Okay, on your homework, you're going to have a diagram that's pretty similar to that. It asks you maybe to go a little bit further than that, but that's kind of the main idea there. Questions on that? Okay, these are the ones that I really struggled with coming up with examples on, and I think these are the ones that when you guys get to your homework, they may be tougher than what I came up with, but I was kind of struggling. So I got kind of the basic idea, but you may have to use your brain a little bit for these ones. Okay, so let's do a triangle that looks like this. isosceles triangle, so we'll mark those top two sides as congruent. Okay, this bottom left angle is going to be x, the vertex angle is going to be y, and the exterior angle is 135. Now, I want to find x and y. So before I kind of come up with a game plan of x and y, we might just want to kind of bring back all of the information we know about triangles, because I got this exterior angle. And I've also got an isosceles triangle. So let's start with the idea, because this is kind of the new part, that this is an isosceles triangle. Why is that important? Or how is that helpful? So this base angle right here is also x, right? We just talked about that. If you have an isosceles, that's the isosceles triangle theorem. If the sides are congruent, the base angles are also congruent. So I don't know what it is, right? I don't know what x is, but I know they're both x, okay? Now once I fill that in, how can that help me find one or both of these? So I know that x plus 135 equals 180, because it's a straight line, right? So if I subtract my 135, we should get x equals 45. So I have x, but if I know x is 45, if this is 45, and this is 45, how am I going to find y? So 45 plus 45 plus y equals 180, right? All of the angles in a triangle add up to be 180. So it'd be 90 plus y equals 180. Subtract the 90, so y equals 90. So x is 45, y is 90. Very good. Okay, number 4. Let's say we have, this time, an equilateral triangle, and I will warn you guys that I don't think this one works out. I copied it from the book, but maybe I didn't think about it a little more, but anyway. Okay, so we've got an equilateral triangle. Now, I know that if it's an equilateral triangle, what else do I know about it? All the angles are also equal, right? What?
How does the book say, like, equal angle?
So if it's equilateral, it is also equiangular. I don't know if I'm pronouncing that right. What?
That's a weird.
It is. Yes, it is. Lots of vowels there together. Okay, so let's say this is y minus 10, and this is x plus 5. Okay, so we said, I know that all of these are equal. So, I mean, one thing I could do is I could say, well, I know that y minus 10 equals x plus 5. But that's not really helpful, because if I don't know what x is, I can't find out what y is. If I don't know what y is, I can't find out what x is. That might help me in the end, but right now it's not going to help me.
Because all of them are equally consistent. The y by itself, and you can substitute that for y.
Oh, so we could do y minus 10 equals y minus 10, or what? Or
You can add 10 and then substitute x plus.
okay, so you're doing, that's actually how I started this one. So, he's doing systems of equations, which is what I did at first, and you can totally do systems of equations. Now, there's a way to do this without systems of equations. If you know all of these are equal, they're all x plus 5. What else do I know?
All of them would, including them that's not measured equal 180, and all equivalent, so
Right. You could do that, so you take 185 by 3. Let's do this. This is kind of the more like visual way I think. Okay, all 3 angles are x plus 5. So I've got an angle that's x plus 5, another angle that's x plus 5, and another angle that's x plus 5. What do all 3 angles added together equal? 180, which would be 3x plus 15 equals 180. subtract your 15, you get 3x equals 165. Divide by 3, you get your 45. So once you have your x, this is where you could use this one right here, right? You know if x is 45, 45 plus 5 would give you 50. Add 10, and you should get y equals 60. Okay, like I said, though these were kind of hard to recreate, I tried. But you're going to do similar things when you get to your homework. Okay? Alright, so last thing, let's look at a picture. We're going to have this big, tall isosceles triangle. We will call it triangle A, B, C. We are going to draw, so we'll say AB is congruent to AC, isosceles triangle. We're going to have a bisector from the vertex angle down to the bottom. We'll call that point M. And since that's a bisector, we know that this angle is congruent to this angle. Now with these ones, I figured out in second hour that there are a lot of different ways to come up with the answer. So we'll try to throw all of them out there because I know sometimes some of our brains work differently than others. So let's say if the measure of angle C equals 63. We want to find the measure of angle CAM. If the measure of angle C equals 63, I want to find the measure of CAM. So they give me this angle right here. So if this is 63, what else do I know? Go ahead, Leo.
Angle B is 63.
I also know angle B is 63. What else do I know? I know AM equals AM. That's congruent to itself. What do I know? This was theorem 4-5 that we put in your notes. Makes right angles. Because if you have an isosceles triangle and an angle bisector, this is a perpendicular bisector. I know those are right angles. So this kind of gives you two ways to find, I'm looking for this angle here. One way you could find this angle is just by looking at that right-hand triangle, right? Because you know this is 63, you know this is 90, right? So you would take 180 minus 153, and you get 27. That's one way. Or we could look at the big triangle, right? What would I do if I was going to look at the whole big triangle? Okay, I do 63 plus 63 is 126. What would I do next? Okay, so all of the angles together are 180. So 180 minus the 26 would give me 54, but that's not the same answer. Divided by 2, why? Because there's two angles, and it's a bisector, and if you divide it by 2, then you get 27. Those are kind of the two ways to do that. Make sense? Okay, what about this one? What if we say BC equals 11, BM equals what? If BC equals 11, if that whole thing equals 11, what does BM equal? You?
5.5.
5.5. How did you get 5.5?
I took 11 divided by 2.
You divide it by 2, right? We know that M is the midpoint, right? This is the perpendicular bisector. It's going to cut it in half. So you would take 11 divided by 2, and you'd get 5.5. And last thing, let's say if the measure of angle BAC equals 33, we want to find the measure of angle B. So, think this was kind of confusing in the last class. We kind of take it from problem to problem, so the 63 is no longer a thing, okay? Now, these are still right angles, though. So this time they tell me that the measure of angle BAC, so this entire vertex angle right here, okay? The whole angle right here is 33. I'm looking for the measure of angle B. They got a game plan here.
Divided 42 by 2 and on that person subtract off 180.
So 33 divided by 2, because that would tell you this one. Okay, so that would give you 16.5. And you know this is 16.5. And you know this is 90, right? You would take 180 minus, when you add those together, you get 106.5, and you would end up with 73.5. Another thing you could do, you know all three, if you're looking at the big triangle, you know all three of them add up to be 180. So if you did 180 minus 33, you would get, 147? And you know those two are the same. So if you divide that by 2, you'd end up with the same answer, either way.